Right, this will be the first video of 2 for chapter 11, looking at gases. As a preview, this PowerPoint will look over the kinetic molecular theory, and that's a theory for these it's a model for gases where we assume these gases are composed of widely spaced, non-interacting particles who have an average kinetic energy which depends on the temperature. We'll then look at pressure, which is the force per unit area, and this force is coming from the collision of gas particles with the surfaces. We'll also look at gas laws. There are several gas laws, and using these gas laws, if we combine them, we can look at the combined gas law. And from all these gas laws put together, we form our ideal gas law, which combines 4 properties of a gas. It combines the pressure, volume, temperature, and the number of moles in a single equation to show how they are all related. And lastly, we'll look at partial pressures of mixtures. So first, let's relate this idea of the pressure of gases to something that we see in our everyday life. So when we're drinking from a straw, what we're doing is we're removing some of the air particles or the air molecules that are inside of the straw initially. And because we're removing some of the air particles, what we end up doing is we end up reducing the pressure that's within the straw. Now, as we mentioned before, pressure is the force exerted per unit area. So the formula for pressure is equal to force per area, or force over area. Now, pressure is the force exerted per unit area by these gas molecules as the gas molecules are colliding with the surfaces around them. In the case of a straw, as the gas molecules are colliding with the surface of the straw. So a molecule will exert a force whenever it collides with a surface, in this case, the surface of the straw. And the result of all these collisions will be pressure. Now, even at sea level, the gas molecules that are at atmosphere do have an average pressure, which is 101,325 Newton per meter squared, or in English units is converted into 14.7 pounds per inches squared. Now, as we're removing some of these air particles from within the straw, and we said that we're reducing the pressure, that's what's within the straw now, because we have less air particles that are actually colliding with the surface, which is the surface of our straw. What happens is this is now creating a pressure difference between what's inside of the straw and the pressure difference outside of the straw. And this happens by pushing up, or what happens is that the liquid within the straw is now being pushed up by the straw molecules, by the molecules that are in the atmosphere outside of the straw. Remember that air molecules are primarily made up of nitrogen and oxygen molecules. So if we look here, in figure A, we have a straw that's put into a glass of orange soda. But at this point, we aren't sucking any air out of the straw. So the pressure that's inside the straw and outside of the straw is going to be the same. Therefore, the liquid levels that are inside and outside of the straw are also going to be the same. In figure B, we see now a person is sucking on the straw, which ends up reducing the pressure inside of the straw. Again, this means that we've removed some of our air molecules as we're starting to suck the straw. And because of this, the pressure inside of the straw is also lowered. So now what happens is that we're going to have greater pressure on the surface of the liquid outside of the straw, greater pressure than inside of the straw. And because of this, this will now push the liquid inside of the straw up. Now, even if we were to have a perfect vacuum with a pump, the atmospheric pressure could only push orange soda, for example, up to a total height of 10.3 meters. So at some point, at some height, this orange soda can no longer be pushed up. Now, orange soda is mostly composed of water, so we can say the same thing for water. So a column of water of 10.3 meters high will exert the same pressure, which is the atmospheric pressure, 101,325 Newton per meter squared, as the gas molecules in our atmosphere. In other words, the orange soda would rise up the straw until the pressure exerted by its weight is equaled by the pressure exerted by the molecules in our atmosphere. At that point, we do not have our soda height increasing any longer, and it'll just stay at that 10.3 meters. Now, the kinetic molecular theory is going to look at understanding the behavior of these gases. And this model is going to predict the correct behavior for most of our gases under many conditions. Similar to other models, the kinetic molecular theory is not perfect, and under certain conditions it can break down, but we're going to be focusing on the conditions where it does not break down. So for the kinetic molecular theory, we have that the gas is a collection of particles in a constant straight line motion. These gas particles are not going to attract or repel each other. So if we have two gas particles, for example, just moving in random straight line motions, eventually they are going to collide with a surface, and their direction is going to change. In time, what we'll see is that these two gas particles will end up colliding. But this is not because of a certain attraction or repulsion. These collisions, after they collide, they simply bounce off each other and continue just as they were before, just as billiard ball collisions. We also know there's a lot of space between these gas particles compared with the size of the particles themselves. And the average kinetic energy, which is the energy that's due to its motion, of these gas particles is going to be proportional to the temperature of the gas. Now, the temperature is measured in units of Kelvin. So when we say that the average kinetic energy is proportional to the temperature, that is specifically to the temperature in Kelvin. So we see as the temperature is increasing that the particles will end up moving faster, and therefore they'll have more energy. Now, we've learned some properties of gases before, and this kinetic molecular theory is consistent with the properties of gases that we've seen before. Recall that we learned that gases are compressible, that gases assume the shape and the volume of their container, and that gases have low density in comparison with liquids and solids. Looking again at how gases are compressible, we see that gases are compressible because there ends up being so much empty space between the gas particles. So here we have our initial gas state in a certain volume. What we can do is we can actually reduce the volume and compress our gas. What ends up happening is the large amount of volume or space that was in between the gas particles will now reduce, but we still have a large amount of space in between our gas particles. Whereas if we look at liquids, they're not compressible because there ends up being so little space between these liquid particles. We also see that a gas assumes the shape of its container. Since the attraction between the molecules in a gas we can ignore, and since the particles are in constant motion, what ends up happening is that gas is going to expand and fill up the entire container. And lastly, gases have low density in comparison with solids and liquids. And this is also due to the large amount of empty space between the atoms or molecules that make up the gas. Now remember that density equals mass per volume. So when we have more open space amongst these gas molecules, because we have so much open space, that's going to mean that we're going to have less molecules per volume because most of it's going to be empty space. If we have less molecules per volume, that means that we have less mass per volume. And if we have less mass per volume, we have a lower density. For example, if we look at the density of steam at 1 atmosphere pressure and at 100 degrees Celsius, it's about 0.0006 grams per centimeters cubed. Whereas the density of liquid water, which does vary a little bit by temperature, but at 1 atmosphere is about 1.00 grams per centimeter cube. Now going back to pressure, we saw that the pressure formula is force per area. So this is a pressure that's exerted by a gas sample. And this pressure is going to be dependent on the force of the molecules per area of its surface. Now the pressure exerted by the gas will depend on several factors, which includes the number of gas particles within a given volume. So we see here at the top container, we have the same volume in both these containers, top and bottom. In the top container, we have less number of particles, or we can say less number of moles of particles, of our gas particles. Because we have less number of gas particles, they will end up having less collisions with the surface. And because of this will give a lower pressure as compared to our bottom figure. In our bottom figure, our container now has more gas particles which will have now more collisions with the surface. And because of these higher collisions with the surface, we'll have a higher pressure. Now we've discussed some of the units of pressure, but there are several that we may be working with throughout this semester. The simplest unit of pressure is the atmosphere, denoted by ATM, and that's the average pressure at sea level. So the average pressure at sea level is equal to exactly 1 atmosphere, or 1 ATM. The SI unit of pressure is called the Pascal, denoted by a capital P lowercase a, and that's denoted by the SI unit of force, which is a Newton. So it's 1 Newton per square meter, which is our area here in terms of meters squared. Now the Pascal ends up being much smaller of a unit of pressure than atmosphere is. Specifically, for every 1 atmosphere, that's equal to 101,325 pascals. In our next slide, we'll look at some more units of pressure, but know that at table 11.1, this can help you with a lot of your conversions in your homework between the different units of pressure. So a third unit of pressure is called the millimeter of mercury. So millimeter, we know, is denoted by a lowercase mm. And mercury, its atomic symbol is Hg. So the unit of pressure, millimeters of mercury, is denoted by mm capital Hg. And this originates from how pressure is measured within a barometer. So within a barometer, we have the average atmospheric pressure at sea level pushing down outside of the barometer onto the mercury. And this pressure that's exerted onto the mercury ends up pushing up the mercury up to a height of 760 millimeters. And 760 millimeters, if we were to convert that into inches, that is 29.92 inches. So if we're talking about mercury being at 760 millimeters of height, we write that as 760 millimeters of mercury for the pressure. This is equal to, if we were to change the millimeters of mercury into inches of mercury, this would be equal to 29.92 inches of mercury. Now, since 1 atmosphere pressure will push a column of mercury in a barometer to a height of 760 millimeters of mercury, we can say that 1 atmosphere and 760 millimeters of mercury are equal to each other. So that is that the conversion between 1 atmosphere unit of pressure is equal to 760 millimeters of mercury of pressure. There's another unit, which is called a torr. So a millimeter of mercury is also sometimes called a torr, which is named after a physicist by Torricelli. And he's the one who invented the barometer. So every 1 millimeter of mercury is also often called 1 torr. Other common units of pressure include the inches of mercury, as we saw on the last slide, and pounds per square inch. Pounds per square inch can be denoted by PSI. For every 1 atmosphere, we saw on the last slide, that's equal to 29.92 inches of mercury, and 1 atmosphere is equal to 14.7 pounds per square inch, or PSI. Let's have some practice with these different pressure units. Take a minute or take some minutes and stop the video as you practice this. All right, I'll be doing number 2 and 3, but I will provide the answers for 1 and 4 for you to be able to check your own answers with for practice. So for number 2, we have 0.45 torr, and we want to convert that into a certain amount of millimeters of mercury. So we start off with our 0.45 torr, and we know we want to convert that into units of millimeter mercury. So we know we want to cancel out our torrs, and we want to convert into millimeters of mercury. And for every 1 torr, that's equal to 1 millimeters of mercury. So now our torrs cancel out, and we end up with 0.45 millimeters of mercury. Now let's do number 3. We're starting off with 1.5 atmosphere, and we want to convert this pressure into pressure units of inches of mercury. Now for this problem, there'll be several different conversion factors that we have to go to until we can finally get into inches of mercury. So we're starting off with our 1.5 atmosphere. We want to end up with a certain amount of inches of mercury. So oftentimes you can find on the internet or going through your textbook, you might be able to find a direct conversion, but for your exam, you're not going to have all of your conversions available. So you will not have a direct conversion from atmospheres into inches of mercury available. So the conversions that we will have is from atmospheres into millimeters of mercury. So we want to cancel out our atmospheres. I want to convert into millimeters of mercury. And we know for every 1 atmosphere, we have 760 millimeters of mercury. So now our atmospheres have canceled out. Now we want to cancel out our millimeters of mercury. And we can convert our millimeters into centimeters of mercury. We know for every 1 centimeter, we have 10 millimeters. So now we can cancel our millimeters of mercury. And currently we're dealing with centimeters of mercury. And lastly, in order to convert from centimeters of mercury into inches of mercury, we have to remember that for every 1 inch, that's equal to 2.54 centimeters. So every 1 inch of mercury, that's equal to 2.54 centimeters of mercury. So now we've canceled out our centimeters of mercury, and we're left with units of inches mercury. And this gives us an answer of 45 inches of mercury. Now for practice, I encourage you to do numbers 1 and 4. The answer for number 1 is 1.6 times 10 to the third torr. And for number 4, the answer is 1 atmosphere. Now let's look at some of the relationships that exist between gas properties, and these are described by the different gas laws. The first of the laws that we're studying is called Boyle's law, discovered by Robert Boyle, and that looks at the relationship between volume and pressure of gas. Now, Boyle's law assumes that we have constant temperature and that we have a constant number of gas particles. So with Boyle's law, what we see is that the volume of a gas and its pressure are inversely proportional. So if we were to write that out, volume is proportional to 1 over pressure. So as volume goes up, pressure must go down. Or as volume goes up, pressure will go down. I'm sorry, if volume goes down, pressure must go up. So if we look at a J2, we see that if we're adding mercury in part A to the J2, what ends up happening is that causes the pressure of the gas sample to increase and its volume to decrease. So here's our initial J2. Now we add some mercury, and what happens is by adding mercury, we're causing the pressure of the gas sample, which is here, we're causing that pressure to increase and the volume to decrease. Plot B looks at the relationship between volume and pressure, and we see that as volume is decreasing, pressure, which is our x-axis, is actually increasing. Now, kinetic molecular theory explains the observed change in pressure. So we see that when volume of a gas sample is decreased, so as we're decreasing the amount of volume, so we're pushing down on the top part of this pistol, we still have the same number of gas particles, but now as the volume has been pushed down, we now have the same number of gas particles, but now in a crowded and smaller volume. What ends up happening now with the same number of gas particles but in a smaller volume is now we're going to have more collisions with the wall of the container. And if we're having more collisions of the wall with the wall of the container, we end up having an increased amount of pressure. So with Boyle's law, we saw that volume is inversely proportional volume is inversely proportional to 1 over pressure, or the inverse of pressure. Inversely pressure is proportional to the inverse of pressure. If we're relating the same gas at 2 different pressures and 2 different volumes, we can actually relate them using this law, or this rule here by Boyle's law. That is, that our pressure, initial pressure, or P1, and our initial volume, V1, the product of these two will be equal to the product of your final pressure, P2, and your final volume, V2. So in our problem, say we're given our initial pressure, our initial volume, and our final volume, and we want to find out what our final pressure is. We can now use this law and solve for P2. So let's try an example problem looking at that. So a sample of gas here has an initial volume of 3.95 liters at a pressure of 705 millimeters of mercury. If the volume of the gas is increased to 5.38 liters, what is the new pressure? Again, we're looking at 2 different pressures and 2 different volumes, so we know we're looking at Boyle's law. Stop the video here and try this problem. All right, we said because we're dealing with 2 different volumes and 2 different pressures, we're looking at Boyle's law, which if we have 2 different volumes and 2 different pressures, its law is P1 V1 equals P2 V2. We have our initial pressure, which is 705 millimeters of mercury. So that'll be P1, 705 millimeters of mercury, times V1 when the initial volume was 3.95 liters. Which is equal to the product of P2 times V2. We do not know yet what P2 is. That's what we're trying to solve for. But we do know what our final volume is, or V2. V2 is 5.38 liters. So to solve for P2, that'll just be the 705 millimeters of mercury times the 395 liters, or 3.95 liters, over, we have to divide the 5.38 to that side, 5.38 liters, and we see that our liters are now canceled out, and we end up with units of millimeters of mercury. So if we plug this into our calculator, we see that P2 gives us 518 millimeters of mercury. So the first of our gas laws that we've looked at so far is Boyle's law, which is P1 V1 equals P2 V2. Now when we consider our second law, which will be Charles' law, that's looking at the relationship between volume and temperature. So let's consider why hot air rises. Hot air will rise because the volume of a gas sample increases at constant pressure as the temperature increases. So as long as the amount of gas, and therefore its mass, are remaining constant, then as we're warming a gas, it'll decrease its density because density is mass divided by volume. So as we are warming a gas, so increasing the temperature, we said that with increasing temperature, the volume of a gas also increases. So that means that our volume here in our density formula is increasing. Mass is staying constant. So if the denominator is increasing, that means that density is decreasing. And this is how a lower density gas floats in a higher density gas, just the same as how wood floats in water, because the density of wood is less than that of water. So heating the air in a balloon will make it expand, following Charles' law. So as the volume occupied by the hot air increases, its density is going to decrease, which allows the balloon to float in that cooler, denser air that surrounds the balloon. Now, Charles, who was a mathematician and a physicist, was the first person to carefully quantify the relationship between the volume of a gas and the temperature. And this relationship is now called Charles' law. He was actually one of the first people to ascend or to go up in a hydrogen-filled balloon. Now for Charles' law, we have to assume constant pressure and a constant amount of gas, or the constant number of moles of a gas. Now with Charles' law, we can say that the volume of a gas and its temperature, specifically in units of Kelvin, that the volume and the temperature in Kelvin are directly proportional. So as we're increasing volume, we will be increasing our temperature, and vice versa. As we increase temperature, we'll increase the volume. So with Charles' law, it can be used to calculate the volume of a gas following a temperature change. It can also be used to calculate the temperature of a gas following a volume change. Remember that for Charles' law, we have to assume that the pressure and the amount of gas are constant. And remember, very importantly, that the temperatures must be expressed in units of Kelvin when you're using this law. So with Charles' law, if we're looking at two different volumes and two different temperatures, we'll have that the initial volume over the initial temperature, so that's V1 over T1, is equal to the final volume, V2, over the final temperature, T2. So let's look at an example problem using Charles' law. Here we have a balloon with an initial volume of 3.2 liters at a temperature of 299 Kelvin, which is warmed to a temperature of 376 Kelvin. What is the volume at that 376 Kelvin? So we see here, we have an initial volume and initial temperature, we have a final temperature and we want to know what that final volume is. So we know that we're using Charles' law. Which is V1 over T1 equals V2 over T2. Remember that temperature must be expressed in units of Kelvin. In this case, the temperature units are already given in terms of Kelvin. So now if we just plug in the information we do have, we have that the volume, the initial volume, V1, is 3.2 liters. And our initial temperature is 299 Kelvin. We want to solve for our V2. And we know our T2, our final temperature, is 376 Kelvin. So to solve for V2, on the left side, we have to move our 376 Kelvin. That was on the denominator of our right side. We need to move that to get it out of the denominator. So we'll need to multiply it over to the left side. So we'll have 3.2 liters over our 299 Kelvin. And now the 376 Kelvin is being multiplied over, and it's going to be in the numerator. And this is going to give us our V2. Notice our units of Kelvin are canceling out, and we'll end up with units of liters. When we solve for this problem, we multiply our 3.2 liters times 376 divided by 299. And our answer comes out to 4.0 liters for our final volume. Now we've looked at Boyle's law, and now we've looked at Charles' law. In our next video, we'll begin by looking at the other gas laws